Welcome to The Critique. Today we're dissecting the OBINexus project, an attempt to bridge legacy COBOL banking systems with a symbolic AI called Trident, all centered on a protocol of encoded suffering.
And that bridge's integrity is questionable. Let's get right into it, starting with the logical determinism in the Trident verification state.
Okay, so looking at the maybe state, the user has this trinary logic system: yes, no, and maybe. And my read is that maybe is meant to be a holding operation, sort of a pointer to a pointer that holds memory indefinitely.
It is. It's almost philosophical. But I have to ask, have we really thought through the consequences of indefinitely in, a high-frequency system?
What do you mean?
Well, the source material frames maybe as infinity to the power of -1. And that's a beautiful mathematical abstraction for waiting. I'll give it that. But in a safety-critical environment, an indefinite hold isn't deep thought. It's a deadlock.
That's the space lock you're talking about from the docs?
Exactly, a space lock. It freezes space and time for that process. So if the system hits this maybe state without some kind of forced exit, you're not pausing the transaction, you're creating a resource sink.
And the Libpolycall daemon just hangs?
It just hangs, waiting for a consensus that might never arrive. I mean, the risk here is that we're so focused on the philosophical right to say maybe that we're ignoring the real computational cost of it.
I see it. The system needs to hesitate, but it can't hesitate forever. So the first real critique is that the maybe state absolutely requires a rigorous time to live, an exit condition.
Yes, to prevent it from getting stuck in an infinite recursive loop, we have to implement a consensus threshold. Or maybe a decay function.
A decay function. What would that look like practically?
We can build on the user's own work. What if we actually use that epsilon to unity growth factor? The text mentions the 1e- metric.
Operationalize it. You mean?
Let's operationalize it. Assign a specific decay value to any transaction that enters the maybe state. It's like a radioactive half-life for indecision.
So the longer it sits in maybe, its value degrades based on that 1e metric.
Exactly. And here's the concrete part. If the Trident verifier, the third node, can't resolve the heterogeneous data into a homogeneous consensus within that time frame, the system has to force a resolution. It has to auto-resolve chaos.
And chaos is the delta less than 0 condition from the math.
Right. And triggering chaos sounds awful, but here it's a safety valve. It kicks off the enzyme repair operation. You're essentially treating maybe not as a parking spot, but as a decaying orbit. If it can't stabilize, it gets rejected to the repair queue instead of freezing the entire mainframe.
That makes perfect sense. It turns a potential system crash into a managed error. Okay, let's move on. The structural integrity of the execution order. We have Cisco, which is bottom-up, and Risco, top-down.
This is where the ontology is really clashing with the architecture. The idea of bridging old and new is strong, using a Unix daemon to submit JCL to the legacy system, but the documentation treats Cisco and Risco like philosophical stances.
And the weakness is, there's no hard interface to find between them.
Not a clear one. It's not at all clear how the Libpolycall daemon is supposed to interact with the flash sequence versus the filter sequence.
Flash being mutation, and filter being sorting.
Right. Flash is creative, filter is administrative. And if you don't define that interface, the Cisco order could misinterpret a legacy batch job as a single flash event.
Okay, and let's drill down on that. What's the disaster scenario if that happens? If this bottom-up logic from Cisco sees a static pank report and treats it like an AI prompt.
Total data corruption. You're trying to mutate a historical record. A batch job from a COBOL mainframe is read-only. It's static. If the daemon applies flash logic to that, it might try to fuse it or change it, which you just can't do in banking.
So the distinction between Cisco and Risco needs a concrete mapping layer.
It has to have one. So our suggestion is to architect a translation layer, or you could call it a middleware adapter.
The notes mention a flash buffer. How can we use that to build this adapter?
We have to define that buffer rigorously. So, for example, when the daemon pulls a report, let's say it calls DFH money on the mainframe, that data packet has to be explicitly tagged as static filter data.
It tells the system, read only.
Exactly. You can look, you can sort, but you cannot change.
And then we reserve the flash capability for, what, user inputs?
User inputs, REST endpoints, anything that is explicitly meant to be dynamic and mutable, that's where you allow the Cisco, the bottom-up logic, to apply.
And what about RISCO, the top-down instructions?
We have to prevent RISCOs from ever mutating that legacy data. You enforce a filter-only lock on any data packet that originates from a legacy PID, a process ID.
So if it comes from COBOL, it's stone. If it comes from the user, it's clay.
The system has to know the difference, instantly.
That seems absolutely vital. Okay, let's talk about the math. The suffering equation, it's defined as suffering equals need minus resources, all multiplied by a constraint coefficient. S equals N minus R times K.
It's a fascinating model for technical debt, almost biological. But, well, there's a huge mathematical hole in it.
Let me guess. The constraint coefficient, K.
Yes. The source says, and I'm quoting, if K goes to infinity, we go to hell regardless. Which is a powerful statement, about systems or the human condition. But in a technical architecture, leaving K unbounded like that is just reckless.
And K is derived from external constraints, right? Circumstances?
Correct. So picture it, a market crash, a DDoS attack, K spikes. Now, if K gets huge, it just amplifies the difference between need and resources. And if your resources are lower than your need, you get a massive negative number. But what if the logic inverts?
You brought up imaginary numbers before we started. Is this it?
This is it. A sudden external load could actually flip the logic, causing the system to calculate negative resources. And that creates these computational imaginary numbers, where you absolutely need factual integers. You can't transfer imaginary money based on a suffering calculation.
So the core weakness is that the suffering algorithm lacks dynamic range clamping for K.
Exactly. It needs to be bounded.
So we need to normalize these variables. I mean, the author talks about debuggable cognition. To me, that means the system has to be able to explain why it's suffering, not just scream.
Debuggable cognition. That's the key. So the fix is simple. Implement a clamping function for K. Even if external stress is through the roof, K should never exceed a value that would make the result of N minus R computationally undefined.
And can you give a concrete example for normalizing the other variables? Resources are, for instance?
Yeah. The NSEIGI text mentions 512-byte segments. Let's latch onto that. Define R, resources, as available CPU or RAM blocks, or literally those 512-byte segments. Don't let it be an abstract concept. Make it a byte count.
And then tie it back to the quadratic formula roots from the text?
Yes. The user notes the positive root is the build path. So we make sure the suffering calculation always feeds into the discriminant, the delta, of that formula. This lets the system check if it's in order, delta greater than 0, or chaos, delta less than 0.
So instead of going to hell when K spikes, the system just calculates the delta is negative, recognizes a chaos state, and triggers the right protocol?
Exactly right. It makes the suffering computable instead of catastrophic. And the cognition stays debuggable because you can trace which variable in R or K pushed you into chaos.
This leads us perfectly into the last piece, verification. This whole three-player chess idea for verifying data. Alice, Bob, and the verifier, Ez.
It's a clever take on the Byzantine generals problem, using XOR logic and a trident ruling. But the source material itself points out the confusion when you're trying to resolve heterogeneous data versus homogeneous.
Heterogeneous being mixed data types.
Yes. The text gives an example. Alice sends an O, but Bob receives an I. Or, text versus binary. The problem is the current lexical analyzer accepts implicit policies.
An implicit is not a word you want to hear in security or finance.
It is not. Implicit policies let noisy data pass through the flash sequence unchecked. The text talks about brown noise or corrupt messages, confusing love and hate. In banking, if you confuse credit and debit because of a type mismatch, it's game over.
So the weakness is that the three-player chess approach is missing a standardized schema for the verifier.
It's missing the rulebook. The verifier needs to know exactly what game it's supposed to be refereeing. Otherwise, the XOR logic might technically pass, the gate says true, but the payload is complete garbage. We have to enforce strict typing at the front door of the Triton interpreter.
And the user's rational wheel framework, how does that fit in?
We use the rational wheel as a sanitizer, a pre-flight check. Before Alice and Bob even attempt the XOR operation, the data has to pass through that rational wheel rotation.
Sort of like a centrifuge.
Exactly like a centrifuge. If the input is heterogeneous, text mixed with binary, the filter sequence has to split them into distinct homogeneous batches. Text goes to the text processor, binary to the binary processor. You never, ever XOR text against binary.
And the third player's role in this?
The verifier doesn't just check for yes-no consensus. It has to check for structure. And we should use that NSIGI human rights tag function from the codebase.
That's an interesting name. What is a human rights tag in this context?
It's a metadata tag. We need to ensure every single packet has a valid tag like NSIGI HR verified before the Trident interpreter even touches it. If the tag is missing or doesn't match the schema, the third player kills the handshake right there. No implicit trust.
Okay, so to summarize the path forward for the OBINexus project.
It's really about taking these powerful, high-concept metaphors and grinding them down into rigorous, enforceable architectural constraints.
So first, the maybe state.
Implement a time to live with the 1e to the dk factor. No more infinite holds, no more space locks.
Second, the execution order.
Map Cisco and Risco to hard read-write permissions. Use a middleware adapter so flash logic can never touch static legacy data.
Third, the suffering equation.
Clamp the k variable. Normalize n and r against actual system metrics to keep the cognition debuggable. And stop the system from calculating imaginary numbers.
And finally, verification.
Enforce strict typing. Use the rational wheel to split heterogeneous data before the three-player XOR revolution even begins.
We invite the listener to implement these constraints into the rectorial reasoning framework. Once you've clamped those variables and tagged your data, please submit the updated OBINexus schema. We really want to see a follow-up on how the enzyme repair subsystem handles the load.
I'm very curious to see if the Trident can actually hold water once all these holes are plugged.
Thank you for listening to The Critique.